Okay, we'll work through problem 566 for statics. See, pen on here. Okay, so we have this rod, it's going to ball and socket at the floor. It's leaning against the wall. It's a smooth rod, so we're not assuming any friction or anything here. And then there's a cord that's attaching that back to the z-axis, or the corner of the room there. So the approach that we'll take here is we'll find the positions of each of these points. We'll use those to make position vectors. Step 3, write our equations of equilibrium. And in particular, in this case, we will have to pay particular attention to our moments here, since there's no moment imposed by this ball and socket joint. So we'll have to make sure the sum of the moments around that point is 0, and that won't be too difficult to do, but it will be a fair bit of arithmetic. And then 4, solve for the unknowns. So we're told in the problem description that the mass of the rod is 20 kilograms. So I'm going to make a point here, center of gravity. I'm going to call that point G, and then this is our weight there. So I'm going to start writing our coordinates for each of these points out. So let me scroll down a little bit. I'm not going to go too far. Alright, so step 1, coordinates. So A has coordinates of, it's right on the x axis here, so it's moved out 1.5 in the x direction. In the y it's moved 0, and in the z it's still at the floor, so it's also 0. Point G, which is our center of gravity, is going to be halfway between that and B. Come back to that in a moment. B, we're at 0, we're on the back wall, so we're on the ZY plane, so x is 0 there. In the y direction we're 1 meter, see that here, and in the z direction we're 2 meters. So G is going to be halfway between here and there, 0.75, 0.5, and 1. So I just took this difference between A and B, took it in half. This difference between A and B in the y direction divided by half, and in the z direction divided by half. And then finally point C, we're back on the z axis here, so we're going to be 0x, 0y, and something in z, 0, 0. So if at B we're at 2 and we add another half to that, we're at 2.5. So those are coordinates. So next we'll make some position vectors. So our first position vector will be from R to the center of gravity, so RAG, or from A to the center of gravity, so we'll call it RAG, and that's going to be our final position minus our initial position. So we'll have negative 0.75 in I. In Y, we're moving out away from the wall a little bit, so we'll be at plus 0.5 J. Then finally we'll have moving up 1K, units of meters. And then I'm also going to go over here. So our magnitude of RAG is going to be the square root of each of those squared. So 0.75 squared plus 0.5 squared plus 1 squared. And that all equals 1.34 6, 3. Next position vector, we'll do R, A, B. So this is from A to B. Why do we need that? So that will help us find our moment of the force from the wall as well as the force from the tension in the rope that creates moments around point A. So that one is going to be negative 1.5 I. So our final position minus our initial position over here, plus 1J plus 2K. That's meters. So the magnitude of that vector, the square root of 1.5 squared plus 1 squared plus 2 squared equals 2.6926. Then finally, we need another position vector for BC here. So we're going to take our final position C minus our initial position B. So we have 0 minus 0, so that's 0I, plus 0 minus 1, so let me make that a negative actually. Oh, excuse me. Alright, so I'm going to make that a negative. Let me scroll back up so you can see the picture. It's going to be negative 1J, and then in the Z direction it's 0.5K. So RBC is going to be the square root of 1 squared plus 0.5 squared. So that equals 1.118. Alright, so there's our position vectors. Oh, I skipped a step here. I also need a unit vector at least for BC. I think I might need it also. I know I don't need it for the others. So let me I'll make this step 2A, unit vectors. So UAG, I'll just do it for all three of them. So it's going to be our position vector divided by our magnitude. So we get negative 0.75 over 1.3463 I plus 0.5 over 1.3463 J plus 1 over 1.3463 K. For AB, we get negative 1.5 over 2.6926 I plus 1 over 2.6926 J plus 2 over 2.6926 K. And then finally, for BC, so we're taking this, dividing by that to get our position vector. So we have 0 I minus 1 over 1.118 J plus 0.5 over 1.118 K. Alright. There we got some of the heavy lifting done. One other point I want to make on here. So if we're looking at the sketch here, at the rod, the base here, we can have a reaction here. I'm going to call that FAZ. We can have a reaction this direction, the X, FAX, and then in the other direction here, FAY. And then up here in the at the chord we have tau BC, and at the wall we have only in the normal to the wall, I'm going to call it NB. And if you notice here, since that wall is in the YZ plane, NB is going to be only in the I direction. So that's going to be helpful in a moment here. Alright, so we're going to write our equations of equilibrium now. Step 3. Alright, so the sum of the forces in X are 0. What does that mean? Well, let me zoom back up here for a second. So what's acting in the X direction? This is the tension in this BC cable is not acting in the X direction. The reaction force here is acting in the X direction. This weight is not acting in the X direction, and this is acting in the X direction. So we can have our normal force at B and our reaction at A in the X direction. So 0 equals NB plus FAX. Sum of forces in the Y direction equals 0. What does that mean? Go back up here. Must need another copy of this photo here. So I have FAY here. This weight is not acting in the Y direction. This normal force is not acting in the Y direction. This tension does have some acting in the Y direction, so we'll have to include that. So 0 equals FAY, and then I'm just going to write these all as positive. If we find a negative sign, it will indicate it's the opposite direction. So in NB, so I'm going to call it tau BC times, I'm going to take the unit vector section of BC here. It's going to be -1 over 1.118 J. So that's just in that J direction. So there's that component. And the sum of the forces in Z equaling 0. What do we have acting in Z? Let's go back up to our diagram. So we have this reaction force, we have this weight, we have some component of this tau, this tension in Z. So we'll include that. So we have 0 equals FAZ minus W plus, I'm going to say tension BC, and it's just the unit vector, the K component of that unit vector, times 0.5 or 1.118. And then, so we've got those three. What's the other equation of equilibrium? Our moment, right? So we can add the sum of the moments, sum of the moments around A have to equal 0. And so what is that going to be? That means the moment due to the, I'm going to say 0 equals the moment due to the weight around A due to the weight plus the moment around A due to the normal force B plus the moment around A due to the tension in BC. I'll have to add up to be 0, right? So we don't have any reaction forces in this. We just have that normal force at the wall, we have the weight, and that tension. Alright, so that's where we're going to do most of the heavy lifting here. So let's see how much room I've got. I can maybe get MAW in here. So I'm going to call this step 3A, calculating the moments. So MAW equals RAG crossed with W. So that equals IJK. What was AG? It was up here a ways. So here's our position vector that we're going to use for that first part. So negative 0.75, 0.5, and 1. Oop, too fast. Negative 0.75, 0.5, 1. And our weight component is going to be 0 here, 0 here. It's 20 kilograms times g, so that's going to be negative 196.2. So we can do our cross product here. So I'll take my I out front. I'll copy my first column over again. Negative 0.75, 0. So I have 0.5 times negative 196.2 minus, what do I have going the other way? 0. So that's all I plus j, we have 0. And going so we have this way minus that way minus 0.75 times 196.2. So these are negative signs, so they make it positive, so I just dropped them there. I'll just add them in here just to make it clear. So negative, negative, j. And then last k, we have 0, right? 0.75 times 0 and 0.5 times 0. So plus 0k. So if I continue with that, when I add that up, I'm going to start on the next page here, MAW, the weight causing the moment around A, so I get negative 98.1 I, so that came from here, the 0.5 times 196.2, and then this becomes a excuse me, 0 minus that. So that's going to be negative 147. 47.5 J. And there's a 0K, so I'm just going to leave that off. Newton meters. So there's one of our moments. I'm going to put an underline under that. Alright, next moment. Moment due to the normal force at B. Oh, I'm going so crazy here. I, J, K. What was our position vector again? I'm going to come back up here. So our position vector is here. Negative 1.5, 1, and 2. Negative 1.5, 1, and 2. And our force, we don't know what it is, but we know it's only acting in the positive x direction, so I'm going to call that NB at I, 0 in the J, 0 in the K. Add my last column over again here. So that equals 0I, right? So 1 times 0 minus 2 times 0. J is going to be plus, let me go here, 2NB, going the other direction, negative 1.5 times 0, 0, J, and then K, so covering up here we have 0, minus, why am I getting it? Minus NB in the K direction, right? So we have negative 1.5 minus 1 times NB in the K direction, so that equals 2NBJ minus NBK. So that's the second moment. We're almost done with the moments. Last moment. Moment around A due to the tension in BC. ijk. What's that position vector again? We'll come back up. We're almost there. Alright, so the position vector BC, 0, -1, 0.5. 0, -1, 0.5. And our tension in BC, we don't know what it is, but we can put it in terms of our unit vector in the tension, right? So you may recall that a force vector equals the magnitude of that force times the unit vector, say A, right? So in this case, we don't know the tension in BC, but we do know the magnitude is going to be the tension of BC, and it's going to act in the direction of our unit vector BC. So that's why we calculated that unit vector up here. So we didn't actually need these AG and AB unit vectors, but we do need this BC unit vector. I've got that written down on my paper, so I'll just transcribe it from there. So we have 0 in the x direction, -1 over 1.118 tau BC, or tension BC, and then we have 0.5 over 1.118 tension BC. So doing our cross product here, we get -0.5 over 1.118 tension BC in the I, and then we're going to subtract that. So we have negative plus negative. Did I mess that up? Oh, I wrote down the wrong unit vectors here. Excuse me. So our position vector from BC, where is this acting? This is where I made the mistake. So this section here is not correct. I'll correct that in a second here. I want to explain why how I made the mistake. So I was using this position vector. That's not correct. So we're doing where the force is acting relative to our moment location. So we're taking the moment around A, so I still should have been using RAB as our position vector. I should not have used RBC as our position vector. So let me correct that down here. Alright, so see if I can get rid of these. Alright, so our position vector should then be -1.5, 1, and 2. So I need to correct this here. Alright, so we're going to have now our position vector. This makes a little more sense. So in I, we're going to have 0.5 over 1.118 tension in BC minus a -2 over 1.118 tension BC, and that's all in the I direction. So there was our, we put our minus sign subtracting this way, and it's 2 times the negative sign, so there's our -2, or negative minus sign. In J, we're going to have 2 times 0. Let me copy this column over. So 2 times 0 minus -1.5 times 0.5. That's it. Makes a plus. So I'll do the math here in my head. Half of 1.5 is 0.75 over 1.118. That's still the tension BC in the J direction. And then finally in the K direction, we're going to have plus 1.5 over 1.118 tension in BC times K. So that's crossing this direction, subtracting off 0K. So if we simplify that down, we get 2.5 over 1.118 tension BC I plus 0.75 over 1.118 tension BC J plus 1.5 over 1.118 tension BC in the K direction. Alright, so this is our moment around A due to the tension in BC. Alright, so now we can add up substitute these into our equations of equilibrium and find our values. So I'm going back up here to remind us where we came from. So here we were with our equations of equilibrium. So we calculate all those moments just for this moment equation of equilibrium. Alright, so let's work through it in the x, y, and z direction. So this is step 4, solve for unknowns. Alright, so we find then that our sum of the forces in the x direction equals 0, or the force in the x direction again, and 0 equals FAX, and in the opposite direction we have the normal force at B, and B equals FAX. Sum of the forces in the y direction equals 0, so we have the reaction at A in the y direction equals 1 over 1.118 tension in the BC direction. So it came from our unit vector. And the sum of the forces in the z direction equals 0. So we had 0 equals the force reaction at A in the z direction plus 0.5 over 1.118 tension BC minus 196.2 newtons from our weight. And then our moments, the sum of the moments around A equals 0. So 0 equals, now I'm going to combine all those moments together. So we had negative 98.1 I minus 147.15 J, and then the around from N8, that was from the weight. From the normal force now at the wall, we have 2 NBJ and minus NBK plus 2 NB, and that's in the J direction, minus NB the K direction. And then last here we have these three terms from our tension moment. So plus 2.5 over 1.118 tension BC I plus 0.75 over 1.118 tension BC J plus 1.5 over 1.118 tension BC K. Alright, and that all equals 0. And back here we had NB equals FAX, so I'm going to substitute that in here to reduce the number of unknowns in this equation. Actually, let's first, I can do that, and then when I solve for the y. So let's look at the I component. So we have this as an I component. This is J, J, K. Here's another I, J, and K. So we can just use our I components. So those have to be equal to each other, or those two have to add up to 0. So we have 98.1 I. So I move that over to the left-hand side. Equals 2.5 over 1.118 tau BC I. So our i's can cancel out. And and then we find that this tension in BC equals 43.87 newtons. So I reported to 4 decimals there, or 4 significant figures. I'll change that to 3 when I finish up my work. The next one, let's see how much room do I have at the bottom here. So in the J direction, so this is in the I direction. In the J direction, what do we have? We have negative 147.15 plus 2, and this is NB. I'm going to substitute my FAX here. And then we had plus 0.75 over 1.118 tau BC, and that all equals 0. You can move the 147.5 to the other side. So 2 FAX equals 147.15 minus 0.75 over 1.118. And my tension BC is 43.87. So FAX equals 58.86 newtons, and that also equals my tension at B, my normal force at B. So we're getting there. We just have left our reaction force at A and the Y and the Z directions. So let's go back up here. So in the Y, that was our J, FAX. So here's our, the last thing we have here is our K's here. So I'll bring those down. So we have negative FAX K plus 1.5 over 1.118 tension BC K equals 0. So FAX, oh, I guess I'm solving for FAX again. So we'll skip that step. Our K's led us to the same solution. So FAY, so now we have our sum in the forces in Y again. So I just had that up here. FAY equals that. Oh, let me just substitute that in. That'll be nice. So from our equilibrium up there, I can substitute this value in now, 1.118 times 43.87 newtons. That's FAY. So FAY is 39.24 newtons. Alright, so then I just have the Z direction left here. Let's forget I have these here. Sum of the forces in Z equals 0. We had that up here. We written out that equation of equilibrium. So FAZ equals 196.2 minus 0.5 over 1.118 tension BC. FAZ then equals 176.6 newtons. So to summarize our solution, we have the FAX equals 58.9 newtons, so just to 3 decimal places, or 3 significant figures now. FAY equals 39.2 newtons. FAZ equals 177 newtons. The tension in BC equals 43.9 newtons, and the normal force at B due to the wall is 58.9 newtons. So those are our 5 unknowns. Oh goodness, I kind of scribbled all over the place there. So it took a little bit of arithmetic to get that worked out. So we've solved for all 3 of the reaction forces here, the wall force here, and the tension in that cord.